If you carry ApoE4, your brain may already be inflamed even in your 30s. This new study shows what's driving it and what you can do. Welcome back to the channel. I'm Dr. Kevin Tran, and today we're diving into 15 cutting-edge insights about ApoE4, Alzheimer's, and brain inflammation, all pulled straight from the Alzheimer's Association International Conference on APOE and Lipid Biology that was held in March 2025. So if you're watching this video as it comes out, it's extremely fresh research. This isn't recycled content or surface-level advice. These are direct takeaways from the top neurodegeneration labs in the world, summarized, simplified, and translated for you, the ApoE4 carrier, who refuses to wait for symptoms to act. We're going deep into immune signaling, lipid metabolism, fibronectin, mitochondrial collapse, and the one molecular switch that may reverse early damage in the brain. And we're going to make it all practical, because knowing the mechanism is only the first step. Let's zoom out for a moment. When we think about Alzheimer's risk, we often picture a single rogue gene, like ApoE4, carrying all the blame. But Dr. Sarah Marzi offers a more layered view. She's not just looking at your DNA, she's looking at what your cells are doing with it. How your life experiences, environment, and even inflammation can flip genetic switches in ways that change the trajectory of your brain health.
I'm an epigeneticist. I study gene regulatory mechanisms in neurodegenerative diseases to really understand how the causal onset risk factors like the genetics and the environmental risk factors are driving cellular programs, cellular memories.
In other words, it's not just about the genes you're born with, it's about how they're used over time. This is the world of epigenetics, the software that runs on your genetic hardware. Imagine your genome as a grand piano. Every key is a gene. You can't change the piano, but you can change how it's played. Now, when it comes to late onset Alzheimer's, Dr. Marzi breaks it down.
So basically, genetic risk for late onset AD is two things. It's ApoE with a very strong genetic effect, and then the rest of it is pretty polygenic, falls into non-coding regions of the genome.
This is huge. ApoE4 is the headline, but beneath that headline is a sea of subtle genetic cues, most of them hiding in the non-coding regions of DNA. These are stretches that don't make proteins directly, but they orchestrate how other genes behave. So what's really driving the disease process behind the scenes?
AD genetic risk is primarily acting through microglial enhancers, and they showed when you look genome-wide at the heritability of late onset AD, it really co-localizes to microglia.
That phrase, microglial enhancers, might sound technical, but here's the metaphor. They are like the light switches that control the behavior of your brain's immune cells, the microglia. So a quick recap here. The microglia are your brain's cleanup crew and security team. They remove dead neurons, fight infections, and manage inflammation. But if the enhancers, those control switches, are faulty, then even healthy microglia start malfunctioning. They might overreact, ignore real threats, or destroy healthy neurons by mistake. That's where the real Alzheimer's risk lies, not just in the genes themselves, but in how the immune system's command center has been wired to respond. This is why ApoE4 is so dangerous. It doesn't just sit quietly in your DNA. In fact, it interacts with these immune enhancers, flipping switches in all the wrong ways. And unless we understand and reprogram those switches, treating Alzheimer's will always be one step behind. Now that we know microglia are key players in Alzheimer's risk, the next big question is, what exactly is ApoE4 doing to these immune cells? Because ApoE isn't just a passive gene, it acts more like a regulatory command center, especially when microglia are under stress. So let's hear what those researchers found.
ApoE is the one with the strongest upregulated effect size. So really, when we're seeing that ApoE is expressed more highly in AD samples, that doesn't surprise me at all.
In everyday language, ApoE4 tells microglia to overproduce the ApoE protein, especially in brains already showing signs of damage. And that's a problem. In a healthy brain, some ApoE is normal. It helps with transporting cholesterol and repairing cells. But in the Alzheimer's brain, too much ApoE4 becomes toxic. It's like flooding the control room with too many instructions. The system goes haywire, microglia start to overreact, losing the ability to tell a friend from a foe. So picture this. It's like a smoke alarm that goes off constantly. even when there's no fire, or a factory machine that starts overproducing, clogging up the system and jamming the output. That's your microglia on ApoE4. This chronic overactivation does three dangerous things. One, it amplifies inflammation in the brain. Two, it interferes with cleanup of toxic proteins like amyloid or tau. Three, it damages healthy neurons nearby. So those are like collateral damage in a war that the brain didn't ask for. So yes, ApoE4 dramatically increases Alzheimer's risk, but not just because it exists, because of how it rewires the microglia into an overzealous trigger-happy force. That's the true danger. And it's why understanding and calming these immune switches may be the key to changing the course of Alzheimer's. Sometimes the most powerful insights come from simple but brilliant design. And this next experiment, it's one of the most elegant demonstrations of how ApoE variants behave in the real brain. So those researchers didn't just study microglia in a dish. They went further. They created a kind of chimera model, basically combining human and mouse biology in a way that let them watch how each ApoE version actually operates inside a living brain.
We used iPSC-derived human microglia xenotransplanted into mouse brains. We used an isogenic ApoE series covering all three naturally occurring ApoE genotypes, so E2, E3, E4, as well as an ApoE knockout.
Let's break that down. So they used iPSCs, so those are induced pluripotent stem cells, from human donors. These were reprogrammed into microglia and then surgically implanted into mouse brains. Each mouse received humans' microglia with a different ApoE genotype. So they either received ApoE2, ApoE3, or ApoE4, and one group with no ApoE whatsoever. It's like installing 4 different operating systems on identical computers. So you have the same hardware, it's the same mouse, you have the same stress level, they have the same environment, but then you notice very different results. And that's here what blew me away. The microglia carrying ApoE4, they were the most dysfunctional. They moved abnormally, they responded poorly to injury, they triggered excess inflammation. Meanwhile, the ApoE2 microglia were calm, coordinated, and efficient, basically like a trained emergency responders. So this wasn't just theory, it was real-time, in vivo evidence that ApoE4 rewires microglia at the cellular level, even when every other factor is held constant. So what does that mean for us? It means that if you carry ApoE4, your brain's immune cells may be primed for dysfunction from the start. Not because of trauma, not because of age, but because the software was faulty from day one. That's why we need to move beyond symptom treatment and start targeting the root immune dysfunction early. This is the power of precision models, and it's changing everything we know about prevention. So far, we've seen ApoE4 rewiring the brain's immune system, but the damage doesn't stop at signaling. It drills down deeper into the engine room of the cell, the mitochondria. Because if your microglia are your brain's first responder, then the mitochondria are the power packs. No energy, no cleanup, no repair, no resilience. And in this next part of the study, one gene in particular sounded the alarm.
One gene that particularly struck out because of strong effect sizes and coming up in multiple comparisons was CHCHD2. This is a mitochondrial protein. The expression over the 4 genotypes, basically you have nice expression in the E2 and the E3, and then basically complete loss of expression in the E4 and in the knockout genotype. So
CHCHD2 isn't just any gene. It's a key player in mitochondrial health and energy production. Think of it like the power regulator in your microglia's engine. In ApoE2 and ApoE3 microglia, this gene is working just fine, keeping the lights on and energy flowing. But in ApoE4 and knockout models, CHCHD2 expression vanishes. The result, cellular brownout. Microglia can't fire up when they are needed the most. The energy grid is completely unstable. This energy crisis makes the microglia sluggish, disorganized, and unreliable under pressure, which means when inflammation hits or when there's injury, your microglia may not respond in time. Or worse, they may respond incorrectly, adding fuel to the fire instead of putting it out. For ApoE4 carriers, this has massive implication. It's not just about genetics, it's about energy resilience. Even if you feel healthy today, your microglia could be running on fumes, making your brain more susceptible to aging, toxicity, and chronic inflammation. That is why mitochondrial support isn't just a biohacker trend. It may be a lifeline for cognitive longevity. And in future scenes, we'll explore how interventions, nutritional, pharmacological, and lifestyle might help recharge these fading circuits. But first, we need to understand what's breaking them. So we've seen that ApoE4 rewires how microglia behave and even how much energy they have to function. But what happens when it's time to clean up? Well, that's why these researchers ran a crucial stress test. Could microglia with different ApoE types actually do their job engulfing bacteria, debris, and damaged brain cells?
We show on the E. coli side, basically the same number of microglia do phagocytose E. coli particles, but the E2 microglia are able to take up more particles than any of the other genotypes. And for the myelin, it's slightly different. So more of the E2 microglia are able to phagocytose myelin than the other genotypes.
Here's what this means. Phagocytosis is how microglia takes out the trash. They roam the brain looking for waste, like damaged myelin, dead neurons, or toxic clumps, and swallow it whole to prevent buildup. But when the researchers looked closely, the difference between genotypes was striking. ApoE2 microglia were efficient, fast, reliable, kind of like New York sanitation crews on a good day. But ApoE4 microglia, they hesitated. They picked up less, and many didn't engage at all. Imagine this, it's rush hour, the city is overflowing with trash, but your garbage trucks are broken down, stuck in traffic, or missing altogether. That's what happens in the ApoE4 brains. Microglia fail to clear out the damage, and that sets the stage for what comes next. Amyloid plaques, tau tangles, and inflammation. So you can see how this is more than just poor housekeeping. It's a fundamental failure in cellular hygiene, one of the earliest signs of neurodegeneration. And for ApoE4 carriers, this breakdown could be happening decades before any symptoms appears. This is why prevention isn't just about supplements or memory tests. It's about protecting your brain's immune system while it's still working. We'll dig deeper into how this dysfunctional cleanup system ties into amyloid in the later scenes, but one thing's already clear, ApoE4 doesn't just add risk, it disables your defense system one microglial cell at a time. Here's a twist I didn't see coming. Buried in the data was a clue about why ApoE2 brains are so much more resilient. And the secret might just be something as simple and sometimes overlooked as vitamin D. Let's walk through what they found.
And the top transcription factor that was enriched for its binding in the ApoE2 genotype was the vitamin D receptor. Vitamin D is known to have anti-inflammatory regulation properties, is that it's contributing to the anti-inflammatory properties of the E2 genotype.
Microglia carrying ApoE2 had more active vitamin D receptors, and they expressed more of IL-10, which is an anti-inflammatory gene that calms immune overreactions. Think of it like a built-in brake system. While ApoE4 microglia tend to overreact and light fires in the brain, ApoE2 microglia can pump the brakes, calming down inflammation before it gets out of hand. Now, here's the kicker for ApoE4 carrier. You might not have the same immunological buffer. Your brain may be primed for overreaction with less built-in control to stop it. That's why monitoring and optimizing vitamin D isn't just a general advice, it's very strategic. Especially if you live in a low sunlight areas, or if you work indoors in an office or have a darker skin tones that synthesize less vitamin D from sun exposure. Well, this isn't about any magic pills. It's about giving your brain the tools to stay balanced, even with a risky genetic hand. And this is what makes vitamin D so empowering. Unlike your genotype, vitamin D is something you can completely change. You can track it, you can supplement it, and possibly rebalance the scales. In later scenes, we'll look at whether boosting vitamin D actually changes microglial behavior, but already we're seeing a blueprint emerge. ApoE2 protects through calm, regulated immune tone, powered in part by this humble, sunshine-driven hormone. All right, quick pause here. If this kind of practical science is helping you decode ApoE4, hit subscribe. It's the best way to stay updated on the next Phoenix deep dive. We've got much more ahead. So far, we've seen microglia in ApoE4 brains struggle to clean up, regulate inflammation, or produce energy efficiently. But what if they're not just weak or passive? What if they're in overdrive, charging around, misfiring signals, and doing damage by being too active in the wrong way?
This is the AD versus control analysis in the microglia. And we see a number of interesting upregulated biological processes, including at the very top cell motility and migration.
So cell motility sounds harmless, but in this case, it's not. Microglia are designed to move through brain tissue to monitor for problems, but in Alzheimer's brain, that movement becomes frantic and chaotic. Instead of slow, careful patrolling, these cells behave like panicked firefighters, sprinting into every room, even when there's no smoke. This hypermobility isn't a sign of health, it's a sign of chronic misdirected activation.
PTPRG, which is a protein tyrosine phosphatase, in a lot of the top upregulated peaks, and it's known to block mitophagy-mediated neuronal death in AD.
The next piece is even more telling. PTPRG is like a built-in safeguard. When neurons are under mitochondrial stress, this gene gets activated to stop them from committing suicide. So seeing PTPRG turned up might sound good, but it's actually a red flag. It means the brain is already struggling to survive, and the system is throwing every possible breaker to avoid collapse. This isn't prevention. It's emergency mode.
We see a number of interesting upregulated biological processes, including at the very top cell motility and migration. And actually, you see this PTPRG, which is a protein tyrosine phosphatase, in a lot of the top upregulated peaks. This peak, we think, most likely regulates CD9.
Add in CD9, another marker of microglial reactivity, and you get a clearer picture. These cells aren't just alert, they are locked in a reactive state, constantly scanning, constantly responding, constantly inflamed. And in ApoE4 carrier, this hypervigilant mode becomes the norm. Their microglia lose the ability to distinguish between damage and normal brain function. It's like their internal GPS is broken, so they keep showing up to the wrong scene, with sirens blaring and no plan.
We see an enrichment for these very low density lipoprotein particles, and that's probably driven through ApoE.
And here's where metabolism collides with immunity. Microglia in Alzheimer's brain show altered handling of VLDL, the very low density lipoproteins, which is no coincidence. ApoE isn't just an Alzheimer's gene, it's a lipid transporter. When ApoE4 is in the mix, these lipid pathways get rewired. Microglia start to treat lipid debris like immune threats and immune triggers like metabolic noise. The result? A system-wide traffic jam. You have immune overactivation, mitochondrial stress, lipid dysregulation, and no clear direction. In ApoE4 carriers, microglia don't just fail at their job. They become overactive, misdirected, and metabolically overloaded. This isn't just wear and tear, it's a dangerous feedback loop. And it might explain why ApoE4 accelerates damage years before symptoms appear. We'll talk more soon about how to break this cycle. But first, we need to keep pulling on the thread and see how this early dysfunction actually begins. So let's circle back to something we touched on earlier, because this one pathway may be at the heart of everything we've seen so far. It's not just about inflammation, it's not just about energy, it's about lipids, the fats and cholesterol that ApoE is supposed to manage.
We see an enrichment for these very low density lipoprotein particles, and that's probably driven through ApoE.
Here's the deal. ApoE proteins are like Uber drivers for cholesterol and fats, transporting them to where they're needed for repair, insulation, and fuel. But ApoE4, well, it messes with the GPS. It slows down the delivery, it reroutes particles to the wrong places, and it causes lipid pileups inside and around microglia. Why does this matter for your brain? Because microglia need cholesterol to build membranes, respond to stress, and clear out damage. When lipid traffic is jammed, their function suffers. And worse, misplaced cholesterol becomes fuel for chronic inflammation, igniting immune cells that were already on edge. This isn't just a heart problem, it's a brain fuel crisis. If you're an ApoE4 carrier, tracking your lipid profile, especially VLDL, triglycerides, and remnant cholesterol, might give you early clues about what's happening inside your brain. And it's why interventions like diet, exercise, fasting, or even medication aren't just about lowering cholesterol. They may actually help retrain this metabolic immune system that's been rewired by your genes. The bottom line is that ApoE4 doesn't just increase Alzheimer's risk through plaques, it does it through lipid chaos. It disrupts the cleanup, it fuels inflammation, and it drains your brain immune energy system. So if you've ever wondered why your labs and cognition feel oddly connected, well, this is the thread that ties them all together. If there's one structure in your body that you really want to keep intact, is this one, the blood-brain barrier. It's a microscopic wall that protects your brain from toxins, infections, and immune chaos. But in ApoE4 brains, this barrier doesn't just weaken, it starts to morph and fail from within. Let's take a look.
But there's a unique population in the single-cell data sets of myofibroblast-like cells in ApoE4 brain.
That sentence should raise eyebrows. These myofibroblast-like cells don't belong in a healthy brain. They are not part of the normal cast of a brain cell types. Their presence means something has gone very wrong. These are stress responders, often found in scar tissue after injury. So what are they doing in ApoE4 brains before major damage even begins? This is where the mystery deepens.
What I've shown you, ApoE4 seems to drive a pericyte to myofibroblast transition. This leads to a change in the ECM, and it leads to amyloid accumulation in the vascular and perivascular space.
Let's decode that. Pericytes are like the maintenance workers of your brain's capillaries. They hug the smallest blood vessels, they regulate flow and reinforce the blood-brain barrier. But in ApoE4 carriers, these pericytes start to shapeshift. Instead of protecting blood vessels, they detach and transform into myofibroblast-like cells. These rogue cells begin secreting fibronectin and collagen. Those are thick, fibrous proteins better suited for wound healing than neural tissue. The result? Well, a vascular system that becomes stiff, scarred, and dysfunctional. Capillaries lose their flexibility, blood flow becomes turbulent, and worst of all, the blood-brain barrier begins to leak. So it's like the flexible support beams in your house suddenly turning into concrete blocks. The building stops breathing, pressure builds up, and cracks begin to form. Here's the kicker for ApoE4 carriers. Once the blood-brain barrier breaks, your brain can't control what gets in or what gets stuck. This means toxins slip past the gate, immune cells flood in unnecessarily, and proteins like amyloid get trapped, forming toxic plaques. So this vascular breakdown isn't a side effect. It's a core mechanism by which ApoE4 increases Alzheimer's risk. And it often starts before symptoms, years, even decades ahead of diagnosis. So the bottom line, if we want to protect brain health in ApoE4 carrier, we can't just focus on neurons. We need to protect the infrastructure, the brain's vascular system, before it's too late. So we've just seen how ApoE4 transforms support cells into scar tissue factories. But what happens to those fibrous proteins once they're released into the brain? Turns out they don't just sit there, they put in trouble.
We developed a vascularized human brain tissue similar to the postmortem brain. We're seeing that there's low levels of fibronectin in the parenchymal space and along the vasculature.
In ApoE4 brains, researchers found that fibronectin lines the blood vessels, and right alongside it, amyloid, not floating freely, but clumped along the vasculature, stuck like glue. Why? Because fibronectin doesn't just create stiffness. It creates a sticky landing pad for amyloid proteins, a bit like velcro stretched across your blood vessels.
In E3 mybrain, if you just expose it to amyloid beta peptides, not much builds up. But if you, before you expose it, you add in fibronectin into this tissue, you can see that significantly more amyloid builds up in the E3 mybrain, suggesting that the fibronectin driven by ApoE4 is actually promoting the amyloid accumulation.
And here's the experimental proof. Even when they took ApoE3 brain tissue, normally more resilient, and artificially added fibronectin, well, amyloid plaques increased. That's the smoking gun. Fibronectin doesn't just coincide with amyloid. It drives it. This makes ApoE4 brains especially vulnerable to cerebral amyloid angiopathy, or CAA, a condition where amyloid builds up in blood vessel walls, increasing the risk of microbleeds, inflammation, and stroke. And this is where it gets clinically important. Anti-amyloid drugs, like those used in Alzheimer's treatment, are designed to clear these plaques. But in ApoE4 carriers, they may rip plaques from already weakened vessel walls, triggering bleeding or edema. So what's the takeaway? If you're an ApoE4 carrier, your blood vessels may already be laced with fibronectin traps, invisible, sticky structures drawing in amyloid years before symptoms. That's why any strategy, whether a drug, a diet, or intervention, needs to account for vascular fragility, not just the plaques. All right, so far we've only talked about a cascade of problems, right? Misfiring immune cells, scarred blood vessels, amyloid trap, but here's the good news. Some of it may be reversible. Let's look at the most helpful data in this entire study.
When we treat the ApoE4 mybrain with TGF-beta inhibitors, we see a reduction of the non-vascular SMA positive cells and an increase of the NG2 positive cells around.
So this is huge. They use the drug to block TGF-beta, a powerful molecular signal that acts like a foreman directing cellular behavior. In ApoE4 brains, TGF-beta goes rogue. It tells pericytes to abandon their post, transforming into scar-producing myofibroblasts. But when researchers inhibited TGF-beta, well, those rogue cells reverse course. Pericytes returned to the blood vessels, myofibroblasts decreased, and the blood-brain barrier began to heal. That's not just slowing damage, that's cellular reprogramming.
This drives a pericyte to myofibroblast transition, leads to increased fibronectin, increased amyloid beta.
Let's connect the dots. Pericytes morph, myofibroblasts appear, fibronectin is secreted, and amyloid sticks like glue. But stop that initial transformation and you cut off the entire cascade. This means drugs that block TGF-beta might do more than protect vessels. They could reduce fibronectin, lower amyloid adhesion, and potentially slow Alzheimer's itself.
Homozygous ApoE4 carriers that are resilient against cognitive decline, a lot of them have mutations in the fibronectin gene.
So here is what is awesome. Some people, like me, carry 2 copies of ApoE4. That's the highest genetic risk possible. And yet, they stay cognitively sharp deep into old age. What is their secret? Well, they produce less fibronectin, or at least it's one of their secrets. A natural mutation blunts this sticky protein, meaning less vascular damage, fewer amyloid traps, and better brain resilience. So, the bottom line is TGF-beta isn't just a player. It might be a master regulator and a druggable one. And fibronectin is not just a biomarker, it's a target. For ApoE4 carriers, this gene may represent something rare in the Alzheimer's story. It represents control, the ability to interrupt the runaway process and reroute the brain back to resilience. So, if you take away just one insight from this entire video, let it be this: Alzheimer's doesn't start at diagnosis. In ApoE4 carriers, the stage is being set far earlier than we think, sometimes before adulthood.
Or looked at young mice around 2 months of age, and strikingly what we saw is that even the young mice, ApoE4 mice, have significant reductions in myelin volume. And so this really suggests that these myelin impairments mediated by ApoE4 might actually have developmental origins.
Let's talk about myelination. That's the process of wrapping neurons in protective insulation, like coating electrical wires so the signal travels fast and clean. In young ApoE4 mice, researchers saw signs of reduced myelin even before stress or injury. That's a huge red flag. It means ApoE4 doesn't just cause inflammation or cleanup failures later on. It quietly weakens the brain's foundation from the very beginning. Later life stresses like infection, sleep loss, menopause, or head trauma don't create the problem. They simply unmask the vulnerabilities that were already baked in. That is why waiting for symptoms is too late. By the time forgetfulness or confusion show up, the damage has often been accumulating for decades. For ApoE4 carriers, this means prevention needs to start early. Not because you're broken, but because your brain runs on a tighter margin forever. The bottom line, ApoE4 isn't just a late life risk factor, it's an early life setup. And that makes early tracking, intervention, and resilience building not optimal, but essential. You can't control the cards you were dealt, but you can change how you play them. Let's take a moment to step back. We just walked through tons of insights that paint a very different picture of Alzheimer's, one that starts earlier, runs deeper, and hits harder for those of us carrying ApoE4. So, ApoE4 risk isn't just about genetics. It's about how your environment and epigenetics reprogram immune cells. 2, ApoE4 rewires microglia to overexpress toxic signals, keeping the immune system on high alert. 3, in ApoE4 brains, microglia become hyperreactive, attacking at the wrong time, damaging health issues. 4, in live models, ApoE4 microglia show the worst behavior. It's sluggish, inflamed, and inefficient. 5, ApoE4 microglia suffers a mitochondrial shutdown, basically losing energy and resilience before symptoms ever start. 6, ApoE4 weakens microglial cleanup, like garbage truck breaking down and letting debris pile up. 7, the ApoE2 advantage is because vitamin D signaling and IL-10 calms the immune system, something that ApoE4 lacks. 8, ApoE4 microglia stuck in overdrive, flooded with stress markers like CD9 and dysfunctional lipids. 9, lipid transport crashes under ApoE4 that fuels inflammation and starve brain cells of clean energy. 10, ApoE4 transforms pericytes into scar-producing cells, damaging the blood-brain barrier from within. 11, that transformation leads to fibronectin buildup, velcro for amyloid that lines up, and clogs blood vessels. 12, fibronectin isn't passive. It traps amyloid and may worsen responses to Alzheimer's drug. 13, blocking TGF-beta reverses this damage. Pericytes return, fibronectin fades, and vessels recover. And lastly, 14, the most sobering insight, ApoE4 begins its damage early, weakening brain insulation before symptoms appear. If we put all of that together, you get a very clear message. This isn't just about late-stage Alzheimer's. This is about what's happening right now in your brain, whether you are 20, 40, or 60. These insights give us the roadmap for what to track, what to optimize, and what to challenge through early action and targeted intervention. That is why in the Phoenix community, we don't wait for symptoms. We run self-experiments, we track changes, we learn from cutting-edge science, and support each other through it all. Because with the right tools and the right people, you can rewrite your story. So if you are an ApoE4 carrier and want to beat the odds and defeat Alzheimer's, check out the Phoenix community. The link to apply is in the description. I review every application personally to make sure it's a great fit. So if you're coming from YouTube, just mention that in your note and I'll make sure to show you some extra love. That's it for today. I hope you enjoyed the video and see you next time. Bye.